Welcome! In this lesson, we will learn how to perform a linear analysis to analyze a solution. We will explain the differences with temporal analysis. In this practice, we will use the simple elevator.a model. Open the model and click on the Simulation tab. After the system compilation is finished, we step into simulation mode. In the contextual toolbar, there are two analysis modes we can select: temporal analysis mode and linear analysis mode. In both modes, run parameters can be set and runs initiated. Temporal analysis mode. That's the default setting. After running the simulation, we can plot graphs of variables and all the results are time dependent. Linear analysis mode. With the linear analysis, the dynamic behavior of the system is studied through the eigenvalues of the system, representing the system nature modes. They allow the prediction of the possible resonances of the system occurring at specific frequencies, as well as the associated damping ratio of the oscillation. The mode shapes, representing the space distribution for nature mode all along the system. They show the parts of the system that are impacted corresponding to a selected nature mode, and they highlight how these parts oscillate. The frequency response, representing the frequency response in gain and phase of an observer variable linked to the excitation of a control variable. They allow predicting the amplitude of the oscillations for various frequencies of excitations. It shows how the nature modes are excited in relation with a selected excitation. The root locus is a plot, real part or imaginary part, representing the trajectories in frequency and the damping ratio of the nature modes due to some parameter changes. Set the linearization times and display frequency domain results for each linearization time point. Frequency domain analysis is faster than a time domain approach, since it does not imply time domain excitations with long CPU time. In the linearization status, the information is stored in the list under the heading Free States, Fixed States, Control Variables, and Observer Variables. Any state variable set to fixed states is excluded from linearization. For the linear analysis, we should set observer variables. For eigenvalues, we should have some free states. For mode shapes analysis, we should have at least one observer and one free state. State observers count as free states. For frequency response analysis, we should set both control variables and observer variables. For root locus analysis, we should perform a normal batch run with one varying parameter, have at least one free state. Let's start to set up a linear analysis. In linear analysis mode, click on the rotary load component to produce the contextual variables tab, or double-click to produce the variable list dialog box. We can change the status of variables. Here, let's set the status of torque at port 1 to control. Click on counter weight and cabin icon. Set the displacement to state observer respectively. Run the simulation. We can select items from Simulate, Linear Analysis, or we can click on Linear Analysis in the contextual toolbar. Eigenvalues. Two oscillating modes are displayed on the lines. You can select the Expand Oscillating modes to view the positive and negative values for oscillating modes on two lines. You can select the Hide Zero Frequency modes to show or hide the zero frequency modes. Model Shapes. Click on the Model Shapes button in the dialog or in the drop-down list of linear analysis. You can select time point and frequency point from the drop-down menu. You can select the observers you are interested in using Shift or Control keys. Now, you can plot the magnitudes. Shift to Energies tab. We can also plot the energies. Click on the Start Pulse Animation button to view the oscillation shape. Close the pulse and dialog. Frequency response. Click on the Frequency response button. If necessary, Select the required linearization time and the result set using the menu. Click on the control variable. The component is highlighted in the sketch. Here, we set the torque of the sheave as the input. In the observer variables, we select the displacement of the two masses as the outputs. Plot and the two peaks are shown in the counterweight displacement curve. The peaks are corresponding to the eigenvalues. As a request, we can also select Nikon's and Nyquist plots. Close the dialog and plots. Root locus. Before starting root locus analysis, let's perform a batch run. Here, we set the friction of the sheave to global parameter. Drag the parameter to study parameters. Go to the Studies tab and set up the batch parameters as follows. Varying from 2 with a step size of 3, with 40 points above. Click OK. Link the parameter by typing COEF into the value. Change the simulation type to batch and run the simulation. Click on the root locus button to produce the root locus dialog box. Select the linearization time as a requirement. Plot to show the results. Give a proper maximum frequency after taking customer scale. Here, we input a value 85. The root locus plot scale is much more appropriate to catch information on frequencies, circles, and damping ratios, straight lines. Close the dialog and plots.